So just to remind you what we have been talking about are semi-simple Lie algebras. And the basic theory that we started out with was every Lie algebra, not just a semi-simple one, but every Lie algebra has a Carta subalgebra of operator of Lie algebra generators H1, H2, HR, which commute among themselves. The maximal set which commutes among themselves. So this is for all ij between 1 to r. And what we are looking for are representations of this Lie algebra as a whole, not just the Carta subalgebra, but all the operators in the Lie algebra. But what we are going to look at are essentially just the operators which form the basis of the Lie algebra. Because if you know what the basis does to a space, you know what every operator does to a space. Every element of the Lie algebra does to a space. Okay, so if we're talking of any vector space V on which carries a representation, what we have are operators on that vector space corresponding to every one of the Lie algebra elements, and we want to figure out what these operators do to the vectors in the vector space. Now, what we are going to do often is we are going to choose these operators to be Hermitian, at least the Carta subalgebra generators to be Hermitian. And this is a big abuse of notation. What I really should use is not HI, but this HI really stands for some linear operator corresponding to HI, right? That is, HI are the abstract Lie algebra elements. What we are talking about are the Lie algebra, are the corresponding representatives which are acting on that vector space. But hopefully, this will not really be a problem because you should be able to figure out from the context what we are talking about. So when we are talking about a particular vector space, when I say the operator HI, I mean the linear operator which represents HI in that particular representation. So since these are representations of the Lie algebra, that means they obey the same commutation relations as the original Lie algebra commutation relations. In particular, these operators HI are Hermitian operators which commute among each other. So they will have a set of simultaneous eigenstates. And these simultaneous eigenstates we will call, or eigenvectors actually in this space. States is a bad habit because we are just essentially imposing quantum mechanics, or at least the language of quantum mechanics, on what we are really doing. But these are really just vectors in your space, which are characterized by labels. The labels, as always, when you're talking of eigenvectors of certain bunch of operators, the labels will be the eigenvalues. But the eigenvalues may not be enough to label all of them, so you may need extra labels. So there's X are the extra labels. These mu's form the eigenvector. So just hold on a bit. Okay, so I'm back after a quick call. Anyway, so these mu's are the eigenvalues. So what happened? I seem to have suddenly lost my pen's action. Can anybody see my screen? Are you still here?
Yes.
My pen seems to refuse to write all of a sudden. Let's see. Okay, let me just close this. Okay, so it has stopped responding. What happened? This is sort of giving up on me all of a sudden.
Sir, I called Monica. She has some work. She'll attend
Okay,
Thursday's
that's fine.
class.
That's fine. Okay, the other question before we, as long as we are still short of getting the thing to work. Okay, I have suddenly got my. Okay, before that, Thursday is Friday a good time for all of you? Then we can shift to Friday instead of Thursday. Just
It's okay for me, but we have to
ask
ask in
in
the
the
group.
group. Let me know. If not, we will start the Thursday class from 9:30 as before. But if Friday is okay, we'll scrap the Thursday thing. We'll move to Friday. Okay, 10 to 12. If that's okay with everybody. Just ask and find out. I seem to have a bit of a problem with this right now. I don't see why. What I'll do is I will just log out and log back in. Okay, so okay, I'm back here. Is my presentation visible? Is my screen visible?
Yes.
Okay. Hopefully this should work. Anyway, I've lost whatever I had before written before, but anyway, the idea was we have operators in your space, Hermitian operators which commute, so they have a simultaneous set of eigenvectors, and they're labeled by the eigenvalues mu I. Of course,
Sir, we lost your presentation.
that's what I was. Yeah, I hope this is back. Let's see the Zuna
Yes.
screen, right? The pad on which I'm writing.
Yes.
Okay. So this is basically what we had, and we have one mu for each one of the operators, and this forms an element of an r dimension, small r dimensional vector space. Just hold on, I will have to open the door. Okay, so these are the weight vectors for this particular representation. So these are called weights. And when we want to talk about the way in which our Lie algebra or generators, or actually operators corresponding to the Lie algebra generators, go and act on a vector space in a particular representation, then of course we are actually focusing on these weights. Okay, and these eigenvectors play a very important role there. Now, specifically, if you look at this one representation, the adjoint representation, then things become even more interesting in a sense that in the adjoint representation, of course, the operators are really not the operators that we talk about are not the Lie algebra generators. The adjoint operators corresponding to the Lie algebra generators. And because of the fact that this is a representation, we do have the fact that add HI's commute. So they have a set of simultaneous eigenvectors which are generators of the Lie algebra themselves. And this is how the thing works out. And this really, of course, means the commutator of HI with E alpha is alpha I E alpha. Okay, so everybody remembers this, right? Now, just to point out that when, since Georgi, for example, the book from which I'm taking most of this from, Georgi uses this notation for the Lie algebra operator or the representatives of the Lie algebra generators, in particular the Kata subalgebra generators, in this form, right? He uses the letter for the Lie algebra element itself for the operator and uses a ket-like notation to talk about the vector. Of course, that's basically because he wants to use Lie algebras in particle physics, so quantum mechanics plays a big role in his presentation. Now, so that is why what he does is that when he talks about a relation like this, he wants to write it as HI, the same HI, acting on E alpha would produce alpha I E alpha, but this will, of course, be completely misleading because HI E alpha already has a meaning, right? You see, the point is, you are saying that this operator goes and acts on your vectors to produce new vectors, right? So HI E alpha, of course, means the product of the operators HI and E alpha, and especially if you're using it in the quantum mechanical sense, HI E alpha already has a pretty well understood meaning, which of course is not what we are talking about here. So either you could say HI commutator E alpha is alpha E alpha, which is perfectly right, or say add HI acting on E alpha is alpha E alpha. But if he insists on using HI acting instead of saying add HI acting, which is what he is doing throughout for consistency, he has to say, okay, this is a different kind of action. So these are the operators and this is your vector. The vector happens to be nothing but the Lie algebra generator. And the operator here actually is the operator representation of the HI operator, which of course is the add HI operator. So this is just I'm sorry, I think I over-explained this and made it a bit more confusing than it really should be. But all that I'm trying to say is the reason why Georgia uses a notation like this when all he means really is HI commutative with E alpha is alpha E alpha, is that he wants to be consistent for all representations. He is using this notation HI acting on a vector gives you a multiple of that vector. So he sticks to that throughout. But of course, what he really means is this. So we also saw one thing that E alpha dagger has to be E minus alpha. Well, strictly speaking, it has to be proportional to E minus alpha, right? Because HI E alpha dagger is of course minus alpha I E alpha dagger. So E alpha dagger and E minus alpha can at best differ from each other by a multiple, by a multiplying factor. However, we define E alpha, E minus alpha to be E alpha dagger. And in particular, we take this normalization E alpha E beta or in general, we are using the general normalization between operators. Which if you have two operators x and y on your space, you normalize this by using trace of x dagger y. This is the inner product, or what Georgia has done is just to be consistent with every standard application that people have used quantum this for. He has put in a factor in front. You're allowed to put in any factor you want, in the sense that you can show that ultimately, okay, you may say, why keep the KD at all? Because this D, of course, means that it is a different factor for different representations. Is there simply for convenience? You can, of course, absorb the KD in the definition of the generators by adjusting by them, rescaling them by 1 by root KD. However, it's not done simply because in many, especially in particle physics applications, these generators have physical meaning. And sometimes if you want to sort of give the eigenvalues the direct physical meaning, then the normalization that we would love to have, that is a factor of 1 here, may not be the most convenient choice. So you have a representation dependent scale factor. And in particular, the factor that he uses, or he insists that if you're in the adjoint representation, then that factor is called lambda. So this is what going to be, and he insists on this particular particular normalization, which is, of course, a choice, and this is a very convenient choice. It's not just Georgia who does that, it's more or less the standard choice. Okay, so why are these operators E alphas important? We have already seen that. E alpha acting on mu x d. Of course, when I say E alpha acting on mu x d, I again mean the operator corresponding to the shift generator E alpha acting on that vector space. This, when you apply hi on that, you get mu plus alpha's ith component E alpha mu x d, which essentially means mu plus alpha I, or the vector mu plus alpha, is a weight unless E alpha, of course, these all have arrows on top, but I may just not use arrows. So unless the shift operator kills a particular vector space, you have got a new weight. So if you start from a given weight, you shift them by roots, you get new weights, or you get 0. And coming back to the adjoint representation, again, I'm just, if any of these results seem unfamiliar to you, you should tell me, but this is something which we have all seen before. E alpha, E beta, you can easily use a Jacobi identity to show that E alpha, E beta is also going to be a shift operator of the form E alpha plus beta. Either it's going to be 0, or it's going to be some constant n into E alpha plus beta. In particular, E alpha and E minus alpha, the commutator, will have a root of 0, which means it has to be a Karta subalgebra element. So it has to be a linear combination of the Karta generators, and we showed that it has to be specifically this. And so going back, we could start with for every root. So this works for every root, or rather, strictly speaking, for every root pair, alpha minus alpha, you have this result that alpha dot h, and you will just scale it with alpha mod square. That's just to make it make the generator look nice in the end. And you use alpha by mod alpha as E plus, and E alpha by, sorry, E minus alpha by mod alpha as E minus. We have 3 operators for every root pair alpha minus alpha. You have 3 operators, E3, E plus, and E minus. which form an SU2 subalgebra of the entire Lie algebra. So every root pair gives rise to an SU2 subalgebra. And the commutation relations can be figured out very easily. They work out to be plus minus E plus minus, and E plus commutator with E minus works out to be E3. Okay, the existence of this SU2 subalgebra gives rise to several important results, with some of which we have already seen. For example, we have seen that each root vector corresponds to a unique generator. I think, Anurag, you messaged me about this. I think either I may have miscommunicated or you misheard. What I really meant is this, that if you have a weight vector in a given representation, that weight vector can, of course, still not be completely specified after you specify all the weights. That is, even if you know mu1, mu2, mu3, up to mu r, that may not be enough to completely specify the vector that we are talking about, which is why you have those extra labels x in the notation. But when you're talking of root vectors, then those extra labels are no longer needed, because what we managed to prove, using the fact that there are SU2 subalgebras, that each root vector has to correspond to a unique generator. Okay? So there is no, in the adjoint representation specifically, where we are talking about the root vectors as the weights, there the root vectors are enough to uniquely label your generator or your vector, which in this case is a generator. Okay? I hope all of you remember the proof, right? No response. You remember the proof or don't remember the proof?
Yes, sir.
Anyway, even if you did not remember, I'm not going to repeat that again. You can watch the video again if you want. Anyway, that's one result. Another result is basically, if alpha is a root, then the only non-zero so alpha and minus alpha are the only multiple pairs. 2 alpha, 3 alpha, 1.37 alpha, these cannot be roots. Okay, so that's already a huge restriction. Again, I hope everybody remembers the proof. And then going on to any general representation, we had this result that if you applied the operator E3, remember, is alpha dot h by mod alpha square. And of course, although I'm writing a single E3, there's one E3 for every alpha, or rather every alpha minus alpha pair in your theory. So here you have E3 acting on mu xd, that you can easily apply alpha dot h on that and just use the definition to end up with alpha dot mu by mod alpha square mu xd, which means every one of these weight vectors, not the weight vectors, but the eigenvectors corresponding to the weights that we were talking about, are actually SU2 eigenstates corresponding to these SU2 algebra. In fact, there are SU2 eigenstates for every one of the SU2 subalgebras. And this immediately tells me that twice alpha dot mu by mod alpha square must be an integer, because that's something we know about all SU2 subalgebra representations. So I'm just borrowing from results that we already know from angular momentum. And in particular, if you start with a state mu xd, we have already seen that you start with mu vector, and let's just drop the x because that's to be understood anyway. If you apply E plus on this, E plus, after all, remember, apart from a rescaling, is nothing but E alpha. So if you apply E plus on mu d, it's going to increase the weight by alpha, or it's going to shift the weight by alpha. We are still not in a position to say increase at this stage because we don't know what bigger or smaller is in a multi-dimensional vector space, which this is. This is an r-dimensional vector space, so we have no way of saying which one is bigger, which one is smaller. But E plus shifts, and if you can keep on shifting it, you get newer and newer states. But if you are talking about finite dimensional vector space, so you're talking about finite representations, then this must come to a halt. So there must be an integer p such that this is not 0, but E plus the power p plus 1 mu d is 0. Similarly, E minus shifts in the other direction towards minus alpha, and there must be an integer q such that you can shift below or shift by E minus q times, but not q plus 1 times. You try shifting it q plus 1 times, you end up with 0. And this immediately tells me that the E3 eigenvalues for this state and this state you can immediately calculate and end up with this result, that alpha dot mu plus p, that's what you get for this state, must be plus j minus q has to be minus j for some j which is in fact, well, it's not really z, it's really w, right? Whole numbers. Right, so this is basically what you have, is that you can't just take any arbitrary vector and say that, okay, this is going to be my weight vector for this representation. There may be infinitely many representations. The representations can be very, very different from each other. But no matter which representation you're talking about, in that representation, you cannot have a weight vector which does not obey a relation like this. So this is what you call the master equation, which all weights and all roots must obey. So although this doesn't really look like much, simply because p and q are unknown at this stage, but remember, p and q have to be integers. That puts and positive, non-negative integers, right? So this puts a huge amount of restrictions on the structure of roots and weights. And this is what we are going to actually exploit in trying to understand what the Lie algebra is going to behave like. So any questions so far, or is that all clear? This particular relation, of course, is one of the most important relations that we have. I didn't prove it now, but I have already proved it before, so I hope everybody remembers how the proof came about. Any questions? Okay, so this, of course, can be rewritten by just adding the two together and just eliminating the j. You can write this as minus half of p minus q, which is something which tells you a lot about what kind of angles the root vectors may, the weight vectors in general may make with the root vectors. But as we have already described before, this becomes even more useful when we talk about the adjoint representation. So we are now going back to the adjoint representation. In the adjoint representation, the weights are nothing but the roots. So if you just talk about shifting the root beta, which is also the weight beta in this representation, by using E alpha, then you end up with this result. On the other hand, you can also think of shifting the weight, weight alpha by E beta, and then you will end up with this result. So in one case, I'm using the SU2 subalgebra generated by E alpha, E minus alpha, and alpha dot h. In the other case, I'm using E beta, E minus beta, and beta dot h. But the results, of course, look very symmetric, but the final result that you get out of here is the angle between the two is given by this thing. And since P minus Q and P prime minus Q prime are just integers, these immediately gives you that there are only few angles possible. So theta, alpha, beta, the angles turn out to be only these values, turn out to have only these values. These are the only possibilities in a semi-simple Lie algebra for the angles between the roots. So that, as you can see, is a huge, huge restriction already. So the geometry of the roots is very strongly restricted by all these things that we have. So this is the recap of what we have talked about earlier. I think we have all covered all of this before, right?
Yes, up to this
Up to
point.
this point, we have covered. Now we are going to move on to the new topics. So first thing that we are going to talk about is basically we want to talk about how to say that you are shifting up or shifting down. That is how to talk about weight in the weight space, which is of course a space with smaller dimensions. How do we talk about positivity? So what exactly is a positive weight? In other words, we need to be able to define an ordered relationship between vectors in a smaller dimensional vector space. Okay. So how do we do that? We do that basically by looking at this, that say a vector can be 0, positive, or negative. That's what we want, right? Now there's no absolute way of doing this, or no non-artificial way of doing this. But what we can always do is we can choose an order of the kata generators, that is, which we have already implied, right? When we wrote H1, H2 to HR, we somehow put H1 first, H2 afterwards, and so on. But strictly speaking, all these R generators are on the same footing, right? There's no natural order among them, but I have to choose one of them. And then, of course, that automatically implies an artificial order among the weight vectors. Now, what you will say, a weight is positive. This is a definition. A weight So that's the definition. That's it. You just look. If your first, if mu1 is positive, then it's a positive root, positive weight. If mu1 is 0, if mu1 is negative, then it's a negative weight. If mu1 is 0, then you go on and look at mu2. If mu2 is positive, then fine, is positive. If mu2 is also 0, then you go and look at mu3, and so on. Of course, if all of them are 0, then you have a 0 vector. But that, of course, is neither positive nor negative. But all other vectors, all other weights can be classified this way. Now, why am I saying this is an artificial classification? Yes?
H1, H2 up to HR can be chosen in any order.
Yeah. Right. So you can choose your sorry. You can reorder your H1, H2, HR. And if you reorder your H1, H2, HR, then of course, which weight is called positive can very well change. But once you have fixed a particular order among your HR1, H2, HR, then this is a perfectly good definition of positivity. In particular, this also allows you to say one weight is bigger than another weight simply by demanding that mu minus nu, the difference, is a positive weight. What that means is, well, you compare mu1 with nu1. If mu1 is more than nu1, then mu is bigger. If mu1 is less than mu1, mu is smaller. But if mu1 equals nu1, then you move on to the next component. This, of course, is also called dictionary order or lexical order for the simple reason that's how dictionaries are ordered, right? You look at the first letter, when the first letters match, you look at the next letter, then you go on to the next letter, and so on. So there's a standard lexical order or dictionary order. Okay. Which just as in the dictionary, the first letter, the ordering, you have decided to go by the first letter of the word. Here you're there at least the first letter of a word sort of has a meaningful thing, right? You can't really commute the letters around and still get a meaningful word. Here, on the other hand, you can, of course, shift the components around. It would just depend on how you chose your original H1, H2, HR to begin with. Okay. So now that we have this notion of positive weights, we can now also talk about highest weight states. Or, well, highest weight may not be exactly right, but you can at least say weights which are as big as possible. In other words, you try to shift them by, remember, weights can be shifted by roots, by hitting with E alphas. So, so now, just because this definition can be used for any r-dimensional vector, you could just talk of positive roots, negative roots, and so on. So a highest weight state is one which will be killed by all positive roots. So is that okay? Of course, if it were not killed by all the positive roots, then you could hit with a positive with that particular positive root which does not kill it. You get a new state which has an even bigger weight simply because of the definition of what is bigger and what is smaller. So if you have a highest weight state, it's killed by all the positive roots. Okay. So you don't really have to so to know where you are starting off in a particular representation. Now you should know that the highest weight state is very important because when we did SU2, we started with the highest weight state, kept on hitting with lowering operators and got the entire representation. We are going to try to do something very similar here. The only problem is you'll have more than one SU2. And so there are multiple ways of going from the highest weight state to lower states and so on. But the basic idea is just exploit the SU2 starting from the highest weight state. Okay? SU2s, not the SU2. So identifying the highest weight state is very, very important. And as I've just said, what helps you identify an highest weight state is one which is killed by all the positive root, all the generators corresponding to positive roots. Well, that's true, but you can actually do with less. You don't have to look at all positive roots. You can just look at simple roots, and that's all. So this is our next point. We have to define what is called a simple root. So among all roots, there are positive roots, there are negative roots, and of course, there could also be a zero root, but the zero root, of course, corresponds only to, zero root is not even called as root, but the zero root corresponds to all the Carta subalgebra elements. Okay? So what exactly is a simple root? It's a positive root is a positive root which you cannot write as a sum of other positive roots. So just to understand what this means, let's first look at an example. SU3 would be the best, I guess. Okay, maybe my drawing skills should be improved a bit. Wow. Somehow my hand refuses to go straight now. That's even worse. So basically, you should remember from the lecture on SO3 that you had that these are the roots of SO3. They are placed on 6 corners of a hexagon. Okay, this doesn't really look like 6 corners of a hexagon to me, but anyway. And this is your one axis, this is your two axis. So when you decide on which one is the positive root, which one is the negative root, you go by looking at the one axis first, then look at the two axis. Okay. So for this one, so what happens is, which are the positive roots here? So this one is definitely positive. What about this one?
Positive, since 1 is the first.
Yeah.
So that's why.
Yeah, so this is positive and this is positive, right? Look at the first component. If that's positive, then it's positive. And these are all three are, of course, if it's easy to see that if mu is positive, minus mu has to be negative. And these are all minus mu's for one of these mu's. So these are negatives. Okay, so 3 positive roots in ACO3. Now, among the 3 positive roots, you can actually write this one as sum of this and this, right? If you took this root and this root, added them together, you would actually get this root. So this is not a simple root. But the other 2 positive roots, you can easily see that you cannot get them by adding 2 positive roots. You can, of course, get this one by adding this one with this one. But these are not 2 positive roots, right? You cannot get this particular vector by adding any of the 2 positive vectors. Similarly, neither can you get this one. But you can get this one by adding these 2. So this is not simple, the other 2 are. Is that okay with everybody? Yes? No? Maybe?
Yes, sir.
Okay. So the positive roots are now broken into 2 classes, simple roots and non-simple roots. As it will turn out that you will be able to write down every positive root as a positive integer combination of the simple roots. So if you can find a state which is killed by the simple roots themselves, okay, killed by simple roots is really wrong language. You should say killed by generators corresponding to simple roots, but I will just say killed by simple roots. I think that should be sort of obvious. That's a bad language, but I'm pretty sure you should be able to figure out what I mean by that. So if a state is killed by all the simple roots, it's basically killed by all positive roots, which means it's the highest weight state. Okay. So just looking at simple roots will be enough. In the case of SU3, you don't need to look for states which are killed by all the 3 positive roots. Just these 2 simple roots will do. Okay. But that's really not the reason why simple roots are so important. What is really important is that the simple roots are enough to tell you everything about the structure of the algebra. If you have a semi-simple D algebra, if you just know the simple roots, that's it. You don't need to know anything else. You can actually construct all roots from there. So even in SU3, let's say we did not know that there are 6 roots. We just knew that these are the 2 simple roots. Okay? That's it. And from that, we should be able to reconstruct the entire root diagram. Or not only that, we should also be able to figure out the entire algebra. That is, what are the commutation relations, not only of the Karta subalgebra generators with these elements, which of course you already know, right? Because H1 commutator with this is alpha 1, H1 commutator with this again is H2 commutator with this again is alpha 2 for this one, and so on. If you know the know the roots, you know the commutators with H. But the commutators with of these generators among themselves, of course, when I say commutator of roots, I mean commutators of generators corresponding to these roots, among themselves can also be figured out just from the knowledge of the simple roots. So this is why simple roots are so important to learn about. Okay? And what I'm going to do is I'm going to jump ahead a bit and say something about diagrammatic representation, which is important, which is this. Okay, we will come to let's talk about that a bit later. First, so simple roots are important, and why are they important? We are going to see that soon. We are going to talk about what makes them important. Okay, but first some properties. Alpha minus beta is not a root. I'm not even saying it's not a simple root. I'm saying it's not a root. Okay. So why am I saying that? That actually is very, very simple. Look, if alpha and beta are simple roots, what does that mean? That means that they are positive roots which cannot be written down as sum of other positive roots. Okay? But alpha is of course beta plus alpha minus beta. Okay, does that contradict the fact that alpha and beta are simple roots? Alpha in particular is a simple root? Yes or no?
If alpha minus beta is a root, then alpha is expressed as a summation of a simple root and a root.
Yeah, but
So
does
alpha
that simple root is a positive root, right? So beta is a simple root, is a positive root. So alpha is what? Is that a problem? Because it's possible, always possible to write a root as a sum of other roots. If it's a simple root, you cannot write it as a sum of two positive roots. Beta is a positive root. Beta being a simple root is positive. Remember, simple roots are subclasses of positive roots. The set of simple roots form a subset of positive roots. This is positive. But is this expression enough to say that alpha cannot be simple? Or you have a contradiction with alpha being simple?
It would have been a contradiction if alpha is greater than beta.
True, but that's not always the case. So it seems like this is not necessarily a contradiction because alpha minus beta may be negative. And then there's nothing wrong with with a simple root being a sum of a positive root and a negative root. But there is a contradiction here. So that's what I'm asking you to spot. Where is the contradiction?
Then
Okay.
beta can be written if alpha minus beta is
So beta
negative, then
is alpha plus beta minus alpha. Exactly. The point is either this is positive or this is positive. One of the two. Okay. Of course, alpha and beta are okay. Let me just make this precise. Alpha and beta are distinct, so alpha minus beta is not zero. So alpha minus beta can be either positive or negative. If alpha minus beta is positive, then this line gives you a contradiction. If alpha minus beta is negative, then beta minus alpha is positive. Then this line gives you a contradiction. Right? So if alpha and beta are simple roots, then alpha minus beta cannot be a root. I'm not talking about positive root or negative root. I'm just saying it cannot be a root. And neither can beta minus alpha be a root. For the same reason. Okay? Of course, if beta minus alpha is a root, then alpha minus beta has to be. If alpha is a root, minus alpha is always a root. Is that okay? Okay, so now this actually has some rather interesting consequences. Well, note that if you hit E beta with adjoint of E minus alpha, or just take the commutator E minus alpha E beta, what are you supposed to get? Just to remind you, for any two roots,
beta minus alpha.
E alpha E beta should be E alpha plus beta apart from a factor, or 0. So the point is, this is either a generator corresponding to root beta minus alpha, which you see does not exist, so has to be 0. Okay, clear? So E minus alpha has to commute with E beta, and E minus beta has to commute with E alpha. So this is for simple roots. Remember, now we are not talking of all roots, we are just talking of simple roots. If alpha and beta are simple roots, then E minus alpha must commute with E beta, E minus beta must commute with E alpha. Now, can you see why that's an important result, this particular thing, E minus alpha corresponding to E beta being 0? It tells you something about alpha dot beta by alpha mod square. Can you tell me what? We already know that for any two roots, alpha and beta, any two roots, you have this result, right? Where what does P and Q stand for? P and Q are non-negative integers which tell you how many times you can shift beta in the direction of alpha. Now that alpha is a positive root, we can say how many times can you raise beta in the direction of alpha, and how many times, Q tells you how many times you can lower beta by subtracting alpha from it, right? So this is for all roots, right? But for the simple roots, we have this result that E minus alpha acting on E beta gives you 0. But what is this? This is trying to shift. E minus alpha commuting with E beta is nothing but just telling you that E minus corresponding, when I say E minus, I mean E minus corresponding to the alpha subalgebra. This is must be 0, which means trying to shift by hitting with E minus. Remember, E minus commutated with E beta is nothing but add E minus hitting E beta. That's where the shift comes from. That makes the thing vanish. That means what? That means among this P and Q, what does it tell you about P and Q?
Q is 0.
It tells you that Q has to be 0. For simple roots, you cannot lower a root beta in the direction of alpha. Okay, if beta and alpha are both simple, which means this has to be minus half P. Well, it actually works both ways. This has to be, yes? How much?
Half Q.
No.
Up Q prime.
Well, Q is 0, right? This is minus half P prime. Again, you can shift alpha in the direction of beta in the positive direction. How many times? That depends on the particular Lie algebra. Okay, different Lie algebras have different values for P and P prime. Okay, but these are integers. That's important, non-negative integers. What is very, very important is that you cannot shift them down. What that means is this is going to be minus half P, this is going to be minus half P prime. So you might say, what's the big deal? I already knew that this was minus half P minus Q, this was minus half P prime minus Q prime, and that gave us a lot of information about the angles between alpha and beta. But actually this does more. Notice that what this is telling you is this. First of all, it's telling you that alpha dot beta by mod beta square. Sorry. Okay, let's just try to multiply the two relations that we have and take the square root. and try to figure out cosine theta alpha beta directly from there. Can anybody tell me what cos theta alpha beta is going to be? Cos square theta alpha beta is going to be 1/4 PB prime. What is cos theta alpha beta going to be? So in other words, what is the big amount of new information which this equation has as opposed to what this equation had for all roots? This is the equation that we had for all roots, right? Minus half p minus q. We see that for simple roots, this has to be minus half p, because q is 0. Was the extra but p is an integer, right? Non-negative integer. P minus q, p and q are both non-negative integers. So what's so special about this relationship? Why do I claim that this has more information in some sense? Or tells me something special about simple roots, which I cannot directly say about all roots? Yes? Something very, very simple. I'm claiming that this tells me something specific about simple roots, which this equation did not tell me. This equation, of course, was valid for all roots. This one, only for simple roots. Yes, it's very simple. What does it tell you about the angle between alpha and beta? You might say, I already have that information. I start with this. And beta dot alpha by mod beta square is minus half p prime minus q prime. And you already got what those angles can be.
Perpendicular.
Perpendicular. Why? Well, first of all, that's wrong because you have already seen the picture a while ago, right?
Yes, yes.
That the angle, how much was the angle for SU2, by the way?
The simple roots had an angle of 120.
Yeah. So perpendicular is out. Well, perpendicular is not out, but perpendicular is not the case for SU2. Okay, forget about everything else. Why is this side different from this side? P and Q are arbitrary non-negative integers. P is a non-negative integer. What's the difference between possible values of this one and possible values of this one? Come on. This is class 2. Okay, not class 2. In class 2, you don't talk of algebra. You don't use letters for numbers. But essentially, it's class 2. That is a class 2. I really means class 2 of school.
Here,
not
P
class
and P prime can only be 0, 1, and 2.
Well, it can be 3, 4, 5, 6, whatever. But yeah.
But 3, 3 and... I mean, 1...
3, 4, 5. I'm not talking about SU2 in particular. I'm talking about all the algebras.
P prime product should be maximum 4.
Yeah, but there you had P minus Q into P prime minus Q prime product. Maximum 4. The PB prime product should be maximum 4, that's true. But that doesn't prevent P from being 10. The P prime could be 0.
Yeah.
Yeah. Much simpler. Class 2, I literally mean class 2 in school.
One will be always negative and
Exactly.
the other can be positive.
Exactly.
Both ways.
Not always negative, that's really not true. But this one, what this tells me is, for simple roots, this thing can never be positive. This one, on the other hand, can very well be positive. There's a P minus Q here, right? That can be negative. That's all. That's the only real difference between this equation and this one. This has to be non-positive, the right-hand side. What that tells me is cos theta alpha beta is always this. Is that clear to everybody? Minus sign is important. When you take the square, of course, when you multiply the 2, you get the square. And in the square, you miss the sign information. That's why you have Well, you had the possibility that cos square theta alpha beta could be half, but that could be 45 degrees or 135 degrees. But here, the only possibility is 135 degrees because this has to be non-positive, right? On this side. You see that? Am I making sense or?
That has a minus q, so this one just has minus half p and minus half p prime. But in the case of non-simple roots, we had minus half p minus q. So that's why you're saying this
Well,
has...
P and Q both had to be non-negative integers, but Q could very well be more than P, right?
Yes, yes.
So P minus Q could be negative. So the right-hand side of this expression could very well be positive. Even that, of course, positive means what? The angle is acute. And there are roots which make acute angles among each other. Let's go back to SU2. There are plenty of roots which make acute angles with each other. These two, for example, or these two, for example, these two, they make acute angles with each other, right? That's very well possible. But simple roots, because they can't be lowered any further by the other simple roots, the angle between simple roots have to be obtuse or non-acute, to be more precise.
Okay, so that's the reasoning you gave for choosing a minus over the plus for minus half root over pp prime.
Yeah, because the minus here is simply because you know both sides are negative. So cos square theta alpha beta you know is 1/4 pb prime. So which square root, which one of the two square roots, which one of the two inverses of the square are we going to use? The negative one, because we know cos theta alpha beta has to be negative here.
Right, okay. Okay.
Okay?
Okay.
And this one, the ratio of the two vectors, the root vectors are also, so the angle between the root vectors are restricted. So what are the possible angles? We already know angle between all roots. We know what the possibilities are. We know that there are 90, 60, 120, 45, 135, 30, 150. But angle between simple roots can be only 90 degrees, 120 degrees, 135 degrees, and 150 degrees. These are the only possible angles. Got it? So that's a huge amount of simplification already. There are only these possibilities, no other possibilities. Okay. And not only that, the length of the root vectors are also restricted. There are ratios of the divide the two. The length of the simple roots are given by this ratio. P by P prime. Sorry. Okay, before we go any further, let's talk of a simple geometric way of representing this, or simple diagrammatic representation, which will come in very handy later. I'm claiming at this stage, I have not proven yet, and I will not manage to finish the proof today, but I'm claiming that the simple roots, at least for semi-simple Lie algebras, if you know the simple roots, you know everything. So it's nice to have a way of representing the simple roots and the geometric information that you have here. And so what you do is you represent simple roots by just open circles. Okay. So SU2, for example, have two simple roots. So you represent them by two circles. Then you talk about the angles between the roots. Okay. So how do you talk about the angle between the roots? How do you represent that geometrically? You simply go in order. There are four possibilities, right? 90, 120, 135, 150. So you say if the angle is 90 degrees between two simple roots, you just draw them as two circles. Of course, remember, a more complicated Lie algebra may have more than two simple roots. Fine, but each pair of simple roots gets an open circle. And then what you do is if the angle between those two simple roots is 90 degrees, you just put them as down as they are, no lines between them. The angle is 120 degree, you put one line between them. So 125, 135, you put two lines. and 3 lines for 150 degrees. So this is the beginning of what are called Tinkin diagrams, which are used to represent, basically they're used to represent Lie algebras, but basically they're really used to represent the simple roots of the Lie algebra. But as I've been claiming, that if you know the simple roots, you essentially know the Lie algebra, at least for semi-simple Lie algebras. So the Tinkin diagrams actually play a very important role. So I'm pretty sure, have all of you seen the book that I'm referring to, the Georgi book? Yes? Anybody here who has not seen the book? I'm assuming everybody has. I hope I'm still connected, right?
Yes.
Yeah. So if you have, the cover actually has a Tinkin diagram. Actually, two Tinkin diagrams for two different Lie algebras. We'll see how to join these together to form all possibilities for semi-simple Lie algebras later on. So we will be able to classify all semi-simple Lie algebras and draw diagrams for all of them. And the diagrams are all you really need to convey all the information, in a sense. So in that sense, it's a very powerful technique. Just by drawing possible pictures, you can get all possible things that you want to know about these things. But that's a long way off, because all we have done so far is shown that these are simple roots. Difference between simple roots cannot be a root. Note that I'm not saying cannot be a simple root. I'm saying cannot be a root. And that tells us something specific about simple roots, in particular that the angle between them is either 90 degrees or an obtuse angle, not just any obtuse angle, because these are only these 4 possibilities now. Okay? Now, this gives us an immediate additional information, which is all the simple roots are linearly independent. Now that takes a bit of proving because it's not very difficult to prove. It's a very simple linear algebra. The basic idea is this. Now let's consider, in our notation now, alpha stands for simple roots. Okay, not all roots, just simple roots. And say we combine them together. Okay, and we get some vector, let's say gamma. If you're going to prove that the simple roots are linearly independent, what I need to prove is that this combination can never be 0 unless all the x alphas are 0. Okay? Right? That's what we need to prove, linear independence. Of course, the example that we have, that of SU2, you can easily see that these two vectors are linearly independent. They're in two different directions, so they have to be linearly independent. But we are talking of in general for any Lie algebra. Any semi-simple Lie algebra, let's be specific. The simple roots have to be linearly independent. Okay. So how do you prove this? We prove this by starting with this statement that if gamma is 0, okay, why is that?
The first component of the alpha vectors are positive, like either positive or they are non-negative. So
Right. And the alphas are positive vectors, so there are some positive components somewhere. Right? So at the very first non-negative component here for the combination will have only positive contributions if you add this. Okay? Which means you cannot get a 0. Is that okay with everybody? This depends on the fact, not on the fact that alphas are simple roots. It just depends on the fact that alphas are positive roots. You cannot combine positive roots with the positive coefficients, only positive coefficients, and get a zero vector out of them. Okay? Right? So what we can always do, after all, for linear dependence, you don't really need all the x alphas to be positive, right? Okay, you can always say, okay, some of the x alphas are positive, some of the x alphas are negative, and that's why you're getting zero. Right? So this by itself cannot tell us that the system is not the set of the simple roots is a linearly independent set. All we have established is that for gamma to be zero, some of the x alphas have to be negative. So what you can do is break up gamma into two pieces. Let's say gamma is basically sum of this kind of vectors, where these are the vectors for which x alpha is positive, and these are the vectors for which x alpha is negative. Right? So if you call this vector mu, let's say, not to be confused with the root vector, I'm just using a notation here. So x alpha alpha summed over for all positive, take only the positive coefficients, put them together, you call that mu. Take all the negative coefficients, put them together, you call that minus mu. That is, of course, they come with only negative coefficients, so you call that a vector which is minus mu. Okay, so mu is nothing but this term, and minus mu is this term. So what we are going to now claim is that this gamma, which is mu minus mu, a positive vector and a negative vector added together, this will never be zero. But that's not so obvious because it's, but what actually it is, because if you take the square, what do you get? You get mu square. Right? This just remember, these are just ordinary real vectors. So the standard algebra for vectors does work. Now, can you see why this can never be zero? And hence gamma vector can never be zero. Yes?
Do we use the fact that the simple roots are obtuse among each other? But these are linear combinations of the simple nodes, so I'm not sure if that will work here.
Are you sure? Okay. Mu is
The linear combinations are positive coefficients.
mu is x alpha. Okay, let's call this x beta beta, where x beta is negative and with a minus sign. Now what happens? You're right. So, yeah, go expand on that. The coefficients are positive, right? So you form mu dot mu. What do you get? You're going to get minus x alpha x beta alpha dot beta, right? Sum over all positive x alphas, all negative x betas. So what is this going to be? X alpha x beta. What is the sign of x alpha x beta?
Positive.
No, x alpha x beta is definitely negative.
Oh, so
Remember,
sorry.
x alpha x beta is definitely negative. But what's the sign of the overall thing? Alpha dot beta is definitely negative, right? Alpha and beta are simple roots, so alpha dot beta, the angle between them is definitely non-positive. Let's put it that way. Okay. X alpha x beta is definitely negative, right? So this is less than 0. This is definitely negative because x alpha is positive and x beta is negative, right? Alpha dot beta, well, equal to 0. So product is what?
Greater than equal to 0.
There's a minus sign in front, right? So mu dot nu is less than equal to 0. So you're subtracting minus twice mu dot nu from mu square plus nu square. So this is definitely greater than equal to mu square plus nu square. So you're subtracting a number which is negative or 0. So this cannot be 0, right? Something which is bigger than or equal to mu square plus nu square, it's impossible for that to be 0. Okay? Clear? Yes? No? Give me a response.
Yes, sir.
Okay, so that means it's impossible to find a linear combination of the alphas which give you a gamma or give you 0. Sorry. Of course, that's not really true. You can always find a linear combination of alphas which will give you 0, but that combination will have to have 0 coefficients only. You cannot have any positive, negative coefficients. All coefficients cannot be positive. We have shown. Of course, if all coefficients have to be 0, then they are a linearly independent set. That's what we try to prove. But if it's going to be 0, then some coefficients have to be positive, some have to be negative. If it's going to be dependent, and we saw that leads to a contradiction. You cannot get a 0 vector out of that. So simple roots are linearly independent. Now, this is a very important result actually, although it's trivial. It's important because of the application that we are going to talk about, but the result itself is trivial. Okay, I meant to say something else. So, can be written as a non-negative integer that is any where the any root, any positive root. Of course, you might say, then what about negative roots? But that's easy. Roots come in positive, negative pairs, right? So if you can characterize all positive roots, then you have characterized all roots. Is that okay with everybody? What we are claiming is any positive root has to be some non-negative integer combination of simple roots. Period. That's it. So things like alpha plus 2 beta, if alpha and beta are simple roots, or 3 alpha plus 5 beta, and so on.
Sir, wasn't this the definition of simple roots?
Well, actually it wasn't, but it is equivalent. That's why I say this is a really trivial statement. Although, remember the definition of the simple roots is that it is a positive root that cannot be written down as a sum of other positive roots. Okay? That and this statement... This statement is not the same.
In the definition, there was no linear combination.
There was no linear combination. There was a linear combination. There was specifically a linear combination which is banned. You could not write a positive root as a sum of other positive roots. That's what a simple root is. Here we are saying you can write all positive roots as non-negative integer combination of simple roots. By the way, in particular, in fact, we will use this notation which Georgite does. We are going to say, we are going to classify these positive roots as phi 1, phi 2, phi 3, and so on. The k is simply some of these integers. So there will be, of course, that doesn't uniquely specify which root you're talking about. There could be several. But phi 1, for example, is one in which the integers add up to 1. These are all non-negative integers. So if the non-negative integers add up to 1, there's only one way that can happen. Only one of them is 1, the rest are 0. Is it okay? That, of course, is trivial. All phi 1s are positive roots. Because they are simply the simple roots themselves. Right? All phi 1s are positive roots. No problem there. But phi 2, for example, would be alpha plus beta or alpha plus gamma if alpha, beta, gamma are positive roots. Not 2 alpha. Why not 2 alpha?
Root vectors correspond to unique generator. Or
Yeah,
if
but
alpha is a root, then no
if alpha is
non-zero
a root, then is
multiple.
multiple is not a root. So that has nothing to do with alpha being simple. But alpha, of course, a simple root is also a root. So 2 alpha is out of the question. 2 alpha cannot be a root. So note that this doesn't work both ways. You just take all positive combinations or all non-negative integer combinations of simple roots, claim that that's a root. That, of course, will not work. But you already knew that because, after all, the number for finite dimensional Lie algebras, the number of roots is finite. And all possible linear integer combinations, of course, is an infinite number. So only some of these will be roots, but all positive roots will be of this form. But okay, first let's establish this, that all positive roots will have to be of this form. As I said, as Shubhadev said, is really in the definition of the simple roots themselves, but not in that language. So can anybody explain why the definition is the same thing as this one? Remember, the definition of simple roots is a positive root is simple if it cannot be written as sum of other positive roots. So how is that equivalent to this statement that all positive roots can be written down as non-negative integer combinations of simple roots?
As we have a finite number of roots, so we can just separate the positive roots in simpler positive roots and then keep on going this process until we get simple root.
Okay, I guess that's what you are saying the right thing. The basic idea is, okay, if the root is simple, it's already an integer combination. Done. It's 1 times alpha. All other simple roots have 0 coefficient. But if a positive root is not simple, then what does it mean? It means I can write it as a sum of other positive roots. Not necessarily as a sum of other simple roots, but as a sum of other positive roots. But okay, then those positive roots may be simple. If they're not, then you can write them as sum of other positive roots, and since this has to end somewhere because there are only finite number available, you will hit simple roots somewhere down the line. And if you just use that logic, it's easy to see that the only way you can get positive roots is by combining integer roots. By the way, that's not really obvious because of one other issue which I have not stated right now, but which I'm going to state right now. We have shown that the simple roots are linearly independent, but we have not shown this. That essentially means you have exactly as many simple roots as the rank of your Lie algebra, right? Because if they're complete, then they have to provide a basis of the space that you're talking about, and this space has a dimension small r, where small r is the rank of your Lie algebra. Of course, you saw that for SU2. SU2 has a rank 1. There's only one. There's only one simple root basically. All roots are multiples of that. Okay, that's really wrong. Only one simple root which is +1. The other one is -1. for SU2. For SU3, you have two simple roots. It's a rank 2 Lie algebra, but that's not an accident. That you have exactly as many simple roots as rank, that's not an accident. By the way, this is, you might say we already have shown that all positive roots are linear integer combinations of the simple roots. So isn't that enough to show the simple roots are complete? The answer, of course, is no. To be complete, the simple roots have to provide a spanning set, which means every vector in your space has to be something which will commute with, which will be a some linear combination of your simple roots, right? The positive roots and the negative roots are only some of your vectors. They're not all possible vectors in that space, right? Is that okay? Do you get my point? The point I'm trying to make is, just because all positive roots can be written as integer, positive and non-negative integer combinations of your simple roots, and as a consequence, all roots can be written down as integer combination of your roots, does not, of your simple roots, does not mean that the simple roots are going to be necessarily complete because of that. Is this point clear to everybody? Yes? Again, yes, no? Maybe?
Yes.
Okay, but the statement is correct. The statement is simple roots are also complete. And how do you prove that? You prove that essentially by contradiction. That's the simplest way of proving most of these results. If they were not complete, then there would be a vector which is orthogonal to all the simple roots, right? So let's assume so xi dot alpha vanishes for all the alphas. Now, take any root, there's a corresponding E phi, any root phi, there's a corresponding E phi, and take the commutator of xi dot h with that. What is that going to be? Yes?
Sir, what's E phi?
Phi is any root. E phi is the generator corresponding to that root. Any root. Not necessarily simple. Simple, non-simple, whatever. But we have seen that all roots can be written down as the integer combination of the simple roots. That's important. All positive roots can be written down as non-negative integer combinations. Negative roots are just negatives of positive roots. So all roots are integer combinations of simple roots. And this xi we are claiming is a vector in your space which is orthogonal to all the simple roots. If simple roots were not complete, there would be a vector which is orthogonal to all of them. Right? Is that okay? So what is this going to be? This, of course, is nothing but xi hi e phi. The xi dot phi, the vector. What is xi dot phi?
0. Because
Has to
zeta
be
is
0 because phi, although is not a simple root, phi is an integer combination of the simple roots, right? If xi is orthogonal to all the phi's, then xi dot phi has to be 0. So this is 0. So what does it tell you about xi dot h? It tells you that xi dot h commutes with all the e phi's. Fine, but why is that a problem? Yes, if you have an operator in your space which commutes with all the e phi's, And being xi dot h has to come in with all the Karta subalgebra elements as well, right? So what do you have? That's trivial because all the hi is coming with all the hj's. This is trivial, and we have already established that because xi is orthogonal to all the simple roots, xi dot h has to be commuting with all the root generators, all the shift operators. But what happens now? Remember at the very beginning, somebody, I think Anuran asked me this question. I'm not sure who did, or maybe Fazlul, I don't remember who actually asked me this question, but these do form a complete set, right? That is,
This will lead to a contradiction that E5 will be an element of the Carter subalgebra.
no, not really. It doesn't say that. It doesn't say hi commutes with E5. It just says xi dot h commutes with all the E5, it commutes with all the hi. But if you take the look at the hi's and the E5's together, they form a basis set for your entire Lie algebra. Right?
Yes, sir.
Remember, by the way, hi's commute with each other, they have a complete set of eigenvectors. Okay, what I omitted to specify at the beginning, some of those eigenvalues will be zero, but the zero eigenvalues are the ones which belong to the Karta subalgebra themselves. For the rest, you have non-zero eigenvalues, and for those are the ones which are called E5. Okay, the shift operators. Zero eigenvalues are in the Karta subalgebra itself. Having said that, if something commutes with all the E5s and all the HIs, then it commutes with all operators in the Lie algebra, right? Now, why is that a problem? If you have a generator which commutes, if you have an element in a Lie algebra which commutes with everything in the Lie algebra, then what do you have? Why? Because it is an ideal. Does that remind you of something? We already talked about this, right? We say that we are only going to talk about simple Lie algebras. In fact, we are going to only talk about semi-simple Lie algebras. And that's it. Such operators can exist in non-simple Lie algebras, but since we are only restricting ourselves to simple Lie algebras for the time being, such an operator simply cannot exist because its existence would contradict the simplicity of the Lie algebra. You have a generator and all multiples of the generator, which means you have a vector subspace, a subalgebra, whose commutative with every element of the Lie group, every element of the Lie algebra will be within that subalgebra. In this case, being within the subalgebra means if you get zero, that of course in the subalgebra spanned by xi dot h. That would be an ideal, a non-trivial ideal. And a simple Lie algebra does not have a non-trivial ideal. Is that okay? So, roots being complete, this is a very important, simple roots being complete is a very important result. But that result is true only for simple Lie algebras, it's not true in general, which is why the theory of simple Lie algebras is much simpler than the theory of general Lie algebras. Is this okay with everybody?
So in case of general Lie algebra, not be complete.
Then? Sorry,
In case
in case of general Lie algebras, yes.
and the simple roots might not be complete.
Exactly.
Or
Might not be complete.
okay.
It will not be complete in general. Okay.
Okay.
So that's the point. The point is we are restricting ourselves to simple Lie algebras, and that's why we have the simple result that simple roots are all that you ever need to talk about. They not only do they form a set which is linearly independent, not only are all roots positive integer, all roots integer combinations of simple roots, we also have this one extra result that they form a complete set in your vector space. So you know exactly how many of them are there for that. You know the rank of your Lie algebra, you know exactly how many you will have. Okay, the final thing is the construction of the algebra from the Lie algebra. Sorry, from the symbol roots. If you know just the symbol roots, suppose somebody has given you this Dingin diagram, which tells you, okay, these are the symbol roots that you have, these are the angles between them. That's it. Can you use that to reconstruct the entire Lie algebra, which means not only what are the roots, also what are the commutation relations between the generators corresponding to those roots. Okay. So we will do that the next day. I'm just going to briefly show you the basic idea today. And the idea simply is based on what we started with right now. That is this phi k but these alphas are only symbol roots now. K alphas are non-negative integers. And sum of k alpha is k. This just helps us to classify or break up the roots into various levels. We know that all positive roots are of this form. Of course, if I know all the positive roots, I know all the roots. Right? So I will just focus on the positive roots for the time being. But although I know all the positive roots of this form, I also definitely know that all vectors of this form are not roots. Only a few of them are. That's phi 1. All phi 1s are positive roots. Why? Because phi 1 simply means only one of the k alpha is 1, all the others are 0. That means we are talking of one of the simple roots. That's it. Well, phi 2. Phi 2 would be basically alpha plus beta, alpha plus gamma, alpha plus delta, whatever. If alpha, beta, gamma, delta are simple roots, beta plus gamma, beta plus delta, these are the possibilities. Okay. Now it's not guaranteed that all of them are going to be actual positive roots. Okay. So how do we go about? So okay. So alpha and beta simple roots. Alpha plus beta may be a positive root, but may not be a root, right? So what distinguishes the two situations?
Sir, I have a question.
Yeah.
Are all the k alphas greater than 0?
No, not all of them. They're
So
non-negative. That is, they can be 0. Some of them can be 0. Some of them can be positive.
so we will only
So, for example, if you have a rank 4, say, suppose you have a rank 4 Lie algebra, then alpha, beta, gamma, delta are your simple roots, right? In
yes.
fact, come back to even for SU2, phi 1, it's just either alpha or beta, right? So this is 1 alpha plus 0 beta. So 0 coefficient is definitely allowed.
And alpha vectors are our simple roots.
Alpha and beta are simple roots in this notation.
Oh, okay. So phi k are essentially the positive roots that we are looking at.
Yeah, but not all of these phi k's are going to be positive roots. Only some of them are going to be. So if you had, say, 4 simple roots, then phi 2 could be alpha plus beta, alpha plus gamma, alpha plus delta, beta plus gamma, beta plus delta, gamma plus delta. There are 6 possibilities, right? For C2. But not all of these 6. All of these 6 are not necessarily going to be positive roots. Okay. But all roots which fall under the classification phi 2 will definitely be one of these 6 or will have to be in this 6. The question is, how do we know which ones are going to be positive roots and which ones are not going to be positive roots? That's important. Remember, right now we don't know we are not claiming that we know the entire root structure or anything. We are not even saying that we know, we're not even claiming that we know the algebra, the original Lie algebra. Forget the root structure. We're not even saying that we know the commutation relations. You're just saying, okay, we know that these four vectors are simple roots for a rank 4 Lie algebra. That's all you know. The vectors are known, alpha, beta, gamma, and delta. We know nothing else. We know this is a semi-simple Lie algebra. That's what we know. Okay? And we know nothing else. We just know that alpha, beta, gamma, delta are simple roots. Then we know that phi 2, one of these could be one or more of these could be positive roots. In fact, at least one has to be a positive root, as we will see, unless there are no other positive roots in your system. Alpha, beta, gamma, delta are the only ones. But the question is, can I figure out which ones are? And based only on my knowledge about the simple roots and nothing else. Okay? But this is where things come in handy. The results that we have so far. We know alpha dot beta by mod alpha square. How much is that?
Half p minus half p.
Okay. And why? Because we know the Q is 0 for this. Because these are simple roots, right? So you can calculate P from here, right? P means how many times can I shift beta in the direction of alpha? Okay. So if P is positive, what does that tell you? It tells you that you can shift beta in the direction of alpha and you will get a root. Clear? That's where the SU2 subalgebra generated by E alpha comes in. So note that if you know the vectors alpha and beta, then you can definitely calculate the left-hand side here. Right? You don't need to know anything else. You don't need to know the algebra or anything. You're given two vectors, you have to calculate the dot product. You can do that. Plus 12. Divided by the length squared. You're definitely going to get minus half times an integer. Minus half times a non-negative integer. That non-negative integer can turn out to be 0. If it is, then you cannot shift beta in the direction of alpha. So beta plus alpha plus beta will not be a root. Okay? Am I making myself clear here?
Yes.
However, if alpha dot beta by mod alpha square turns out to be positive, that is not turns out negative really, but if p turns out to be a positive integer, it tells you that you can shift up. And that means alpha plus beta will be a root. That will give you a next root. Okay. Now, let me just point out that suppose, how does this work in general? This is for phi 2. And phi 2, the point is we'll just get sum of simple roots, two simple roots, right? But phi 3 could be something like this. Phi 3 could be alpha plus 2 beta. Could be alpha plus beta plus gamma. Could also be 2 alpha plus beta. All these could be one more, right? Alpha plus 2 gamma. Whatever. There are more possibilities. So now the question would be, suppose I know phi 3 is alpha plus 2 beta is a root. Can I use that to get a vector in phi 4? The answer is yes, because all you have to do is take alpha plus 2 beta, which I know is a root, dot it with alpha, now is this going to be minus half? Okay, what is this going to be of the form? This, remember, is a root. Alpha plus 2 beta is a root. Alpha is a simple root, but is a root. So what do you know about a roots dot product of two roots like this?
It will have both p and q because alpha is a root and beta is a simple root. Alpha
Good.
plus 2 beta. Yeah.
Alpha plus 2 beta is root. So it should be possible for you to know how many times you can move. But the point is, okay, you should be able to move down as well. You're right. You should be able to move down. However, you should be, because you know how you have arrived at alpha plus 2 beta, you should be able to know how many times you should be able to move down. Is the point clear? The simple root, you can't move down at all. Is it okay? That's why Q was 0 for the simple roots. You have gone from alpha to alpha plus beta. You know you have shifted once in the ratio of beta. From that, you have shifted again in the ratio of beta, you've got alpha plus 2 beta. Okay? Can you shift down from here along the alpha? If you could, what would be the vector? If you shifted down along alpha plus 2 beta, down from alpha plus 2 beta along alpha, what root would you get? Come on. Again, this is simple vector algebra. Now forget Lie algebra and everything. This is just simple vectors. What happens if you shift alpha plus 2 beta along minus alpha? What do you get?
2 beta.
Which cannot be a root, right?
Yes, 2 into beta. Yes. It
So that
cannot be a
means
root.
that for this particular thing, Q has to be 0. Right?
Yes.
So you know what P is. Again, if P is positive, this shifting, that is 2 alpha plus 2 beta. Of course, this will not work at all, because if this were to work, you will end up with 2 alpha plus 2 beta as your root. Okay, I'm not saying this will not work. This might work if alpha plus beta was not a positive root, which is possible. Then 2 alpha plus 2 beta could be a root, right? Otherwise not. Because this, if you shift it along alpha this way, you will end up with 2 alpha plus 2 beta. Here what you're saying is take a vector in phi 3, try to shift it. Okay, am I losing you people completely?
No, we can choose any other root vector instead of alpha, right? Like,
Yeah, you could do it with all of them and see which ones will give you a positive P. The whole point is, even if you chose beta, for example, say you took beta here, and so you were trying to calculate this quantity. That also will be of the form minus half P minus Q, where P and Q are the non-negative integers corresponding to shifting by the beta subalgebra, beta SU2 subalgebra. Okay? Fine. But since you started with alpha and shifted with beta once, you know you can go back one step at this stage. Shifted with beta again, you know you can go back 2 steps this stage. So you know that for alpha plus 2 beta, the maximum number of times you can go back, go down by beta is 2, right? Is that okay?
yes.
And that means that Q has to be 2 for this. So from the history of how you arrived here, you should be able to figure out how much Q is. And if you know how much Q is, this will tell you how much P is. That will tell you whether you can shift up again or not. That is, it will tell you whether alpha plus 3 beta is at all going to be a vector, a root vector or not. Okay? Going along this way, you will soon be able to find out all the root vectors, because there are only a finite number of them. Especially for the simpler ones, it's going to be pretty quick. Just a quick demonstration for our simple example, which is actually way too simple to really make a lot of discussion. These are the SU2 cases, right? The two ones, two making an angle, two unit vectors making an angle of 60 degrees each other. Okay? So what is alpha dot beta by mod alpha square here? How much is this? Sorry, not 60 degrees, this is 120 degrees. These are two simple vectors. Simple roots. So what is the angle between them? That's 120 degrees. What is this alpha dot beta by mod alpha square? How much? Quickly, how much is this? Two vectors of length 1, angle 120. Come on. You know this, right? Of course you know this. What is the constant dot product of two vectors, two unit vectors making an angle of 120 with each other? Don't tell me I've forgotten what cos 120 is.
Half.
No, it's not half. Cos 120 is not half. Cos of an obtuse angle is of course always negative. It's minus half.
Minus half.
That means, and since these are simple roots, q's are of course 0 for this. So the p here is 1. That simply tells you that alpha plus beta is a root. Okay, so it tells you that this is a root. So this, and this are roots. Okay. But is alpha plus 2 beta, is that a root? We know it's not, because we know SU2, and we know SU3. That is, we know the root structure of SU3. But let's try to figure out this way. If how can alpha plus 2 beta be a root? If it is, then alpha plus beta, should it be possible for you to shift it along beta once? Right? So you might say it's obvious that you cannot shift it along beta once more, because p equal to 1 has already told you that the maximum you can do to shift here from alpha plus beta is from alpha you can shift it along beta once. You cannot shift it along beta twice, because p is just the largest number of times you can shift. And that will be right, but you can also figure it out just by doing alpha plus beta dot beta by mod beta square. And asking yourself how much this is. By the way, how much is this? Come on, how much is this? Alpha plus beta is this vector. What is the angle? What's the angle here?
60.
Yeah, so what is this dot product?
Cos 60 root 3 by 2.
Cos 60 is? Wow.
I'm so sorry.
Cos 60 is half.
Half. Sorry.
And that's minus half of p minus q. But we know what q is, right? Why do we know what q is? Because we know that we shifted once along beta to get from alpha to alpha plus beta. So we know that q is 1. So this already tells you what p is. Which means that this, of course, tells us something we already knew in this case, but this is going to come in handy later on for more complicated situations. It tells you that you cannot shift alpha plus beta in the direction of beta any longer because p is turning out to be 0. Which means E plus acting on alpha plus beta, E alpha plus beta is going to give you 0. Will not give you a new root. Okay. So alpha plus beta is a root, alpha plus 2 beta, which is a different vector, not in the same direction, not a multiple or anything. So it might look like it's possible for that to be a root, but it's not. Okay. So next day what I will do is I will try to start with a more complicated Lie algebra. Complicated simply because, well, not really complicated. The point is this SU3 is way too simple a Lie algebra. That might sound rather strange given the fact that SU3 is about the most complicated Lie algebra that you deal with in particle physics most of the time, at least in initial courses. But it really is way too simple to show the full glory of this method because the thing ends just there. Two simple roots, alpha and beta. Alpha plus beta is the only non-simple positive root. And then since alpha, beta and alpha plus beta have been found, minus alpha minus beta minus alpha plus beta are 3 negative roots, 6, and you have 2 kata generators, that's 8. You're done. Of course, what we have not shown yet is how to find out the algebra between them also from this.
Sir, the-
Yeah.
so in case of any general Lie algebra, what we are doing is we are taking one of the simple roots and then
Not one of the
incrementing.
simple roots. We are taking all the. We are starting by knowing that we know all the simple roots.
Yes,
Okay.
yes. I'm saying for deriving the P and Q.
Hmm.
So we are taking alpha and then shifting it along beta, keeping in mind that once we shift along beta, the Q increases by 1. Another shift increases Q.
Yeah.
Yeah. So uh, in case of a general D algebra, do we take the same approach? Take a
Essentially,
simple.
yes.
Okay.
This essentially is the approach. It's,
Okay.
it just gives you something non-trivial for well, for some other Lie algebras. The SU3, frankly, is way too simple for that. You you have exhausted all possibilities at the very first step. So it doesn't really show off the method in full. So next day, what we will do is we will start with some other Lie algebra, which maybe has a few more complicated roots. We'll stick to rank 2 for the simple reason rank 2 is easy to draw and visualize. So you can draw the vectors. But this method can work for all dimensions. Your method does work for all dimensions. Okay. So we'll talk about that in the next day. Okay, so let's wrap it up today. And so when are we meeting? Just let me know. Okay, if Friday is okay with everybody, then 10 to 12 Friday is fine with me.